Hi, my name's Dan, and today I'm going to be talking through a Boolean Algebra example, which is all to do with Suzi's hipster ice cream van. So in order to understand what's going on in this video, you need to have an understanding of Boolean logic. I'm going to be using the symbols double ampersand for and, double bar for or, and exclamation mark for not. Also, it would be helpful if you come across the Boolean Algebra rules. I'm going to be chucking a couple of those in as we go along. Truth tables. There is a little bit here about truth tables which you won't understand if you haven't done truth tables, but it's not necessary for your overall understanding. And towards the end I'm going to be doing some programming, so if you've done a little bit of computer programming, then this might help you. So here we go. Suzi has an ice cream van, but she set this up as a hipster kind of thing. So instead of going to the hatch, you order by using an app. And you stand at a distance, you order through your app, and then it flashes up some kind of sign when your ice cream is ready and you can go and collect it. Everything is one price, so it's fairly straightforward in that sense. However, restrictions apply as to what you're allowed to have on your ice cream. So you are the person who has been tasked with making the app that sorts out these restrictions. So let's talk through them. So, first of all, you can have a cone or a tub. You can't have both. And you can't have neither, which could get a bit messy, because that could be Suzi's trying to give you the ice cream just into your hand. You've got to have some way of holding it. You must have ice cream. This is simple, of course, otherwise it's not an ice cream. However, it's artisanal Madagascan vanilla. There's only the one choice. That is the ice cream that you can have. Toppings. You can have chopped nuts and raisins. Or you can have sprinkles, or you can have red sauce. Actually, if you didn't want the nuts and you just wanted the raisins, you can have either chopped nuts or raisins on their own if you want. And you can have a flake if you want. However, if you've got a flake, you can't have both nuts and raisins because that's just a bit too much and it's getting too expensive. So that's an extra little rule that Suzi's put into place. Okay. That's quite a lot of constrictions that you've got to the ice cream that you can have. It's to stop people from having everything on their ice cream. So how are we going to sort this out? How are we going to turn this into something that we can use in terms of an actual program? Boolean logic. Let's start by creating some variables. So we have these different parameters that have appeared as we've talked through. You can have a cone, you can have a tub, you can have some ice cream, you can have sprinkles, you can have red sauce, you can have nuts, you can have raisins, you can have a flake. And each one of these can be a binary. It can represent whether or not that element has been ordered, which is quite handy when we're looking at Boolean, because Boolean's all about true and false. So what next? Right, shall we use the truth table? You might know what truth tables are, you might not. If you do, thinking about this, we've got 8 variables. How many cases is that going to be? That's going to be 256 cases. That's a lot of cases. That's going to then give us a huge Boolean expression, which we're going to then need to try and reduce. I think it might be easier to approach this in a different way. In fact, there is an easier way, of course. So what we're going to do is we're going to make a list of the conditions. Each of these conditions needs to be satisfied when somebody is ordering for them to be allowed an ice cream. So you must have a cone or a tub, but not both. You must have ice cream. You can have red sauce or sprinkles or nuts and or raisins. You can have a flake, but you can't have a flake if you've got both nuts and raisins. That's all of our conditions. We've got an and or in the middle of this third condition. That's not very Boolean. Let's expand that out. So you can have red sauce, sprinkles or nuts or raisins, or in brackets it's starting to look a bit more like algebra, nuts and raisins. Actually, let's not forget that you could have no topping at all, and it would be quite easy, with the way that this has been worded, to miss the fact that it would be possible to have no topping. Similarly, you can have a flake or not. You don't have to have a flake. Again, that could have been missed if we weren't careful. So what we're going to do is we're going to turn these statements into much more Boolean-friendly terms, so turn them into Boolean algebra. Let's take them one at a time. So the top one, you can have a cone or a tub, and you cannot have a cone and a tub. So I'm looking forwards a little bit here to the fact that once we've finished turning these conditions into Boolean statements, we're going to be combining them together with and. you have to meet all of these conditions. So condition A and condition B and condition C and condition D and condition E, you must meet all these conditions before you're allowed the ice cream. Because we're combining with AND, if we have ANDs in the middle of our conditions, that's also acceptable. So this first condition, you're allowed it if you have a cone or a tub, but also you're not allowed it if you're asking for a cone and a tub. Okay. Second one, you must have ice cream. That's straightforward. Ice cream has to be true. Right, this next statement is a little bit of a difficult one to deal with because we've got a fairly complicated situation. We can have red sauce or sprinkles or nuts or raisins or nuts and raisins or no topping at all. One way of approaching this would be to look at each allowed combination. So for example, you could have red sauce and not sprinkles and not nuts and not raisins. And this is effectively taking the red sauce, sprinkles, nuts and raisins as if it was a truth table, finding all the allowed combinations, and then you could chain them together with or and put the whole thing in brackets. However, there is an easier way. It might not look easier when we do it, but trust me, this is easier than doing it in the truth table way. So we're going to think about forbidden cases. We're going to think about which combinations you're not allowed. So most combinations actually are forbidden in this. In fact, you're only allowed either red sauce or sprinkles or nothing, or nuts or raisins. And the one that's a combination that's allowed is nuts and raisins. That's the only time when you're allowed two things at once. So most combinations are forbidden. And we could go through each combination and say that is forbidden. So red sauce and sprinkles is not allowed. And so we're going to do this. We're going to take all the different combinations. And there aren't actually that many of them, but it still looks fairly complicated. So as we look through them, you are not allowed red sauce and sprinkles. And you are not allowed red sauce and nuts, you're not allowed red sauce and raisins, you're not allowed sprinkles and nuts, you're not allowed sprinkles and raisins, you are allowed raisins and nuts. Okay, next one. You can have a flake or not a flake. Now this looks a little bit like one of our single variable rules in our Boolean algebra rules. It looks like A or not A is equivalent to true, and in fact flake or not flake is equivalent to true. However, as I've said before, we're going to combine these conditions with ANDs. It's going to be a series of AND conditions. And another of our rules is anything and true is equivalent to that anything. So think about this carefully if you need to, but we can take out the true because it's not having any effect. There we go. We've actually got rid of one of our conditions. Thinking about this in the logical sense, we don't really need to know whether the person who's ordering an ice cream has ordered a flake or not in terms of whether they're allowed it, as long as we're satisfying the last condition, which is you can't have a flake if you've got both nuts and raisins. Otherwise, we don't care whether they've got a flake or not. So this last one, you can't have a flake if you've got both nuts and raisins, is another forbidden combination. So this works similarly to that big list of forbidden combinations that we've got. And you cannot have flake and nuts and raisins. Right, as I was saying before, we can combine all these together with AND operators. That's because each of these represents a separate condition, each of which must be passed in order for the ice cream to be a valid ice cream. So we're just going to put some ampersands, and then we're just going to rearrange that as one great big long statement. There we go. It's quite complicated. So the first thing we're going to ask is, can we reduce this? And the answer is not easily. You can spend a lot of time looking at this and trying to reduce it, but we've got 8 variables in here, and we've ended up with 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. So even if we could reduce it, we're probably not going to be able to reduce it very much. We could spend ages trying, but actually the end result of this is going to be programming. To be honest, it might not be worth our while spending the time from something this complicated to try and reduce it. So let's turn this into a program. If you don't know any programming, maybe this has just been a good example for you in how to use Boolean logic, and you can switch off at this point. So one of the things that we've got is that most of our terms are forbidden cases. And this is quite useful. I'm going to show you a way of dealing with forbidden cases in programming something like this. It would help us, though, if there were all forbidden cases. So let's just list all our conditions. And I've put each one on a separate line, and I've turned it into a font that looks a bit more like programming. However, we can see there are two of these that are not forbidden cases. We've got the top term and the third term. We can actually make sure we get a not symbol at the beginning of both of these by doing a double not. So we know from our rules that a double not is equivalent to the same thing. Not A is equivalent to A. So we'll just put a couple of knots on the front of each of those. And you will see in a few seconds' time why this is useful. So first term, though, we can actually use De Morgan's theory on this, which is one of our pairs of algebraic rules for Boolean algebra. And just to recap that, if you're knotting two terms inside a bracket, then you can apply the knot to each term individually and swap the operator in the brackets between and or. So we're just going to swiftly do that. So we've got not cone, and not tub. Okay, the third term, which is the not ice cream, we can't do anything with because that's so straightforward anyway. So we're going to turn this into a program, as I said, and it's fairly easy to do. So we start by adding a Boolean variable, and we're going to set this to be true. We're calling it isValid because this is going to keep track of whether our ice cream that has been ordered is valid or not. And for each of these conditions, we're going to turn them into an if statement, and we're going to say if the forbidden combination exists, then the ice cream is not valid. So this means we're going to strip off the not at the front of each of them and just replace it with an if. So this is why it was useful to do the double not at the front of those two conditions that weren't negative conditions to start off with. So we've got a series of if statements. These are not complete yet, but in each case, if that condition is met, then we need to set our variable to false. And the way that I've done it here is that we actually have a set of if statements, one after the other. There's no else. They're not combined into one large conditional statement. They could have been, but I find this sort of approach easier to keep track of and easier to make sure that everything's going as it should be. It's also quite easy to add more conditions, to take conditions away in this sort of way of doing things. So the program runs through, it starts at the top, it sets our isValid variable to true as default, and then goes through each of the conditions in turn. If it finds a forbidden condition, it will set isValid to false. So at the end, all we need to do is to check the status of the isValid variable. If our order combination is a valid one, then we can go ahead with the order. So this kind of use of a variable is called a flag, and it's a fairly common way of dealing with complex conditions in programs rather than using one long complicated if statement if you can separate it out into a set of invalid cases. Sometimes you can do this the other way, so it may be more reasonable to have a flag that you set to false initially and then you check through for allowed combinations. So we're just going to do one last thing, which is not relating to the programming, but it is relating to the Boolean logic. So we're going to introduce a new Boolean operator, which is called XOR. And this means A or B, but not A and B. Let's show this in a truth table. So we've got four possible combinations. The results that give us a true result are when A is false and B is true, or when A is true and B is false. And it doesn't give us a true result when both of them are true, and it doesn't give us a true result when both of them are false. So this symbol for this that's often used in programming languages is like a circumflex or a little hat thing. So I just want to take us back to the first condition that Suzi's ice cream van had, which is that you were allowed a cone or a tub, but you are not allowed a cone and a tub. This sounds very much like our XOR operator, and in fact that whole thing could have been expressed as cone XOR tub.